Hello everyone. In this video we are going to talk about thresholding or binarization of images and then morphological operators. So far we have seen reading color images, converting color spaces, and grayscale. Now we're going to make it binary, zeros and ones, black and white. So here we are going to read image Lena, and then we're gonna do all these operations on it, and then for the next part we're gonna have this OpenCV image that has some small artifacts in it, and then we do morphological operators. We need the CV2, we need the NumPy, and for a couple of things here we need this module called Mahotas. So the first thing we can do is, and we should do is, we first convert it to what? To grayscale before we can binarize it. Now here, when we binarize an image, the image is going to be altered. So what I will do, I'm not going to alter the gray image. Instead, I'm going to use the copy method and get a copy of the gray and put it into this image called binary. And then I'm going to what? I'm going to basically apply a threshold to it. And let me rename this to binary simple instead of RC and show that. So here I say binarize using a simple threshold of 125. So a simple thing you can do is guess a number that you want, and then if you say what? You say here you are doing the basically you have this what we call the logical vector, right? Or logical array. So you say compare your binary S against 125. If it's bigger than 125, right? Generate a vectors of ones and zeros and pass them to this binary S. So now basically, or a matrix in this case of zeros and ones, and then pass it to here. So anywhere that this condition is valid, set that value to 255, completely white. Anywhere that it is less than or equal, let's say 125, set it to 0, right? So here I'm making it all black and white basically, and I can make it 1, but remember if it's uint 8, 1 and 0 are no different from each other. So I make it 255 so I can see black and white and say I'm using a threshold of 125. If you don't like 125, use 128, right? Exactly midway or anything like that. So if I do that, what's going to happen, right? So let's go ahead and then see what can happen if you use a threshold of 128. So this is my image, and then this is the threshold of 128, and it's not really that bad. Of course, you're gonna lose a bunch of hair because this area is black. You're gonna use some details here, right? And but it's not too bad, I would say, except for maybe a little bit here. Most of it is not too bad. So sometimes you can be lucky, you just put a number in and it gives you a binary image that is not too bad actually, right? So that's the simplest thing you can do, choose a number. But if you want to do something better than just choosing a number just by guess, like 50% of max, 60%, 20%, there are well-known techniques that can give you a global threshold instead of this number that is a little bit more based on the values of the image, not just use a constant number all the time. One of these methods is the Otsu method, which I have a video under the playlist Computer Vision Image Processing for it, and I explained it. It's based on the bimodal assumption for distribution of light intensities, and then it tries to make the interclass variance as max as possible, or separate the two modes of the light intensity, separate them as much as possible. So if you want to get a number, what threshold to use, you can use this method under the Mahotas module called thresholding.otsu. You pass the grayscale image to it and it gives you a threshold. And then you can use that threshold here. Or there is the other method called Riddler-Calvert or RC method, and you can get that threshold as well, right? So if I run the code, each one of these methods, they are going to give me a threshold. And if I want to show you that, let me run it one more time. Yeah, I have too many things here. So let me go ahead and run it one more time for you. So here is the run, and you can see, let me run it one more time for you with a clean screen. So if I run this for you, that was the image. This is the binary with 128. You see that Otsu calculated for me 114 and Riddler-Calvert almost the same, 114.5. So you see these two methods are giving me very similar thresholds. They say, hey, instead of 128, use 114. That is a better threshold. Now, I can use those thresholds in this simple binarization, and I can binarize it using that, or there is this built-in method in CV2 called dot threshold. So you pass to it the grayscale, you pass to it any number that you want from min to max, let's say, and then you pass to it an algorithm for calculating the threshold. And what this one does, it returns to you the threshold that it found and the binarized version of the image. So it gives you both of them. So with this single command, not only you can find the threshold, you are going to apply this binarization as well. So this command is going to do two things at the same time. So I can say, hey, I want you to do threshold Otsu for me, or do threshold binary or threshold binary inverse, or there are so many different things that you can do, and it gives you a threshold that it found and a binary version of the image. And here you see that the threshold that this algorithm found using Otsu is exactly the same as what that Mahata's thresholding Otsu found for me, and that is what 114. So you see the result is the same. And then this binary image, I can go ahead and show it for you, which you can see here. This is the binary image using the Otsu method, and we'll talk about this later, but this is what I have. This guy is what I have using the Otsu method, right? So whether I took that TM and then I applied it to this code, or whether I directly got it out of the CV threshold, I would get what? A binary image. Now, if instead of this guy, you go ahead and you use this threshold binary inverse, that is going to give you an image where the binary is back, it's opposite of this. So anywhere that is white here is going to be black, anywhere that is black is going to be white. The only important thing is this guy here, this number, if you just leave it as 0, you are not going to get that beautiful of a thing. And let me show you that one here. So here I'm gonna redo this, okay? I'm going to redo this for you. And let's go ahead and run it, but with this threshold binary inverse, see what happens. So that is 128, and this is adaptive. Now look at the threshold. It's 0. Why? Because this threshold binary inverse, this is not a method for calculating a threshold. Okay, this is just saying, hey, anywhere that you have this 0 as a threshold, go ahead and use it. Anywhere bigger than 0, make it 1. Anywhere less than 0, which there is no place, make it 0. So this first number is not really the minimum. This is just an initial guess for the threshold, right? Now, when we use the Otsu method, because Otsu method will calculate the threshold for us, I can just throw in whatever number I want. It is going to change it. It's not going to use this. But if I use this threshold binary inverse, or just the threshold binary, which is going to do something similar to Otsu, right? You have to have a good number here for this threshold. You cannot just throw in a 0. So if I want to use this, or as I said, just the threshold binary, I better pass to this guy here a good number, like what? Like this TM that I calculated from elsewhere. I can do that one, and that is going to give me a good image. Let me run it again. So that's the image. This is the 128, and well, let's see here. This is the opposite of what we have. This is the inverse binary. You see that whatever I had in the past, the black areas are white and the white areas are black. And as I said, if I make it just threshold binary with no inverse, then this is going to be similar to Otsu, right? So let me do that one. Here. You see? And so this is very close to that number I had, 128. This is very close to that, right? Very close. But of course, it's 114 instead of what? 128. So let me get rid of these closing windows so you can have everything next to each other and you can compare, right? I would say it's better that we do it this way. Better to have them all side by side. So now this is the Otsu, this is 128, and you see the difference is not huge, right? This is using a smaller threshold, so you get more white areas compared to this one. But one thing that is very obvious is what? As I said, you're gonna lose some details because you are using one single threshold for the entire image. It's called a global threshold, right? You see here, here doesn't have too much, right? But in some areas, you are losing some part of this foreground person, which is Lena. In these areas, you're going to lose a lot of hair and so on. In these areas, you're going to lose a lot of hair and so on. So in general, using one single threshold and comparing all pixels against that is not the best idea. That's where we can use what we call the adaptive threshold. In adaptive threshold, you divide the image into a bunch of blocks, and each block has its own threshold that your method will calculate. And that way, when you get the image, you see it might not be probably as beautiful as this, but here you have preserved a lot of the foreground. And of course, you have some background noise as well, but you clearly see that you have preserved a lot of the hair and so on. So this is called the adaptive thresholding, which is block by block by block instead of the entire image. And for that to work, what you need to do is to use the method called CV2 adaptive threshold. And what are the things that you pass to it? So here you're not passing a single number, right? As I said, what you need to pass is the grayscale image, of course, the maximum value, then the adaptive method. So here the adaptive method I'm using is called CV2 adaptive threshold mean C, where the threshold comes from the average of each block minus the value of C, and C is this last value. So here, by passing 0, I mean don't subtract anything from the average of each block and use the average of each block as the threshold for that block. Now, what is the size of the block for me? I use 11, so it's going to be 11 by 11. And then here I want to use the CV2 thresh binary so that any number bigger than the threshold is 1, any number less than the threshold is 0. If I showed you, if I use this inverse, any number bigger than threshold will be 0, any number less than threshold will be 1. It acts the opposite way, right? So here I'm bringing the image into 11 by 11 blocks and I'm using the average, right? If I go ahead and subtract something here, then I'm bringing this average of each block down, and so I will get what? I will get more and more white pixels. So you might not necessarily want to change it, especially if you think your adaptive has a lot more white pixels than it should, correct? And then you can change, of course, the size of the block to have. And there is another one here that you can use, and instead of this adaptive threshold mean, it can use a Gaussian, basically average of the values in the block and then subtract C. Okay, I can show you that one as well. So here I added the code. For that one, you need to say adaptive threshold, and instead of mean C, you say Gaussian C. So here I created a second image. One of them I call it binary adaptive mean, the other one binary adaptive Gaussian, and I'm going to show you both versions with the same C and with the same block size. So you see the difference between a weighted average, Gaussian weighted average minus C, and then a simple average minus C. So let me go ahead and show you that one. So here, remember that is 128. This is the Otsu method with 114. And then here we have these two guys, right? And you can see them if you maximize. You see this one is mean C. That is a little bit larger, I would say, size of details. And this one with finer details is the Gaussian one. So here you can see the difference between this one and this one. To me, this Gaussian one is a little bit more pleasant looking than this simple average. And it's kind of, because of that Gaussian thing, it is kind of a little bit less susceptible to noise. One of the things you can do before you binarize an image is to basically apply a Gaussian blurring to the image, which we'll see in the next video, convolution filtering and Gaussian blur. That is going to reduce a little bit of the background noise and then apply some binary, okay? But clearly here you can see all sorts of what? You can see all sorts of different algorithms for binarization. And these are adaptive and then non-adaptive or global methods. The next thing we're going to do is to work on morphological operators, working on black and white images. So here I'm going to read a different image called OpenCV2 ping, and that image has basically some artifacts. It's the same OpenCV image that I used in my previous video, but it has some intentional artifacts that I added to it. And then I'm going to use my binary operators, my morphological operators, to see if I can improve on those artifacts. So some of the methods that here I'm going to show you, because morphological operators, there are lots of them. And here some of the useful ones that you see a lot and use a lot are, one of them is the erosion, then dilation, then there is opening, there is closing, and then there is the gradient. So here I'm going to show you 5 of these methods, and most of the time they need what we call a kernel or a structure element to go along with them. Okay, so what I'll do is I read that image in and I read it directly as grayscale, and then I'm going to use a threshold for it. Okay, and here I use the Otsu method. So I can directly go ahead and pass in a 0 for it. Okay, and that method is going to give me an appropriate threshold for it and a good binary image. And then here, for my structure element, I can create anything that I want. I can go ahead and use this command called cv2 get a structuring element. And then there are 3 shapes that this guy can give me. One of them is a rectangle, the other one is an ellipse, and the other one is a cross. And so here I'm using the rectangle one, and you can pass to it basically any size that you want, 8 by 3. And for this 8 by 3, I can use, instead of that big command here, I can simply use the wands matrix from the NumPy and then pass to it the dimension. That is going to do the same job as this whole big command does, okay? As long as you create a matrix 8 by 3 of all ones, that's all you need over here. So whether I use this top command or the bottom command, the result is the same. But when you do ellipse or when you do cross, it's not as simple. You have to write some extra lines of code to create an ellipse or to create a cross. So for rectangle, it's very simple to create it using a simple wands matrix. Now, what I do is I pass a copy of the binary image to the erode command and to the dilate command, and then I pass the kernel, right? This K is called kernel. Let me add that for you here. So this is your kernel, and then you can go ahead and erode it, which is basically is going to thin out the white areas, or dilate it, which is going to expand the white areas. Okay, so until that part, let me go ahead and show you what I have. So I'm going to save it, and I'm going to run this again for you. Seems like I have some here error. Let's go ahead and run. So these are all of those things. Now let's look at the original image. This is the original image. As I said, that's the OpenCV, and I added some noise in the background and some holes in this 3Cs. So now what I have is, this is the binary version of the image using the Otsu method, which you see it's actually very good. And now that is my binary image. So now I use my erosion, and then I use my dilation. Let me use the dilation and show you this one. And you can see them side by side. Let me get rid of the other things so they are not on the way. Here we go. So look now. If you look this versus this, you clearly just look at this text. That might be easier to see. Look at, this is the original thickness of the text. This here in erosion, you clearly see it's thinned. And then here it is definitely what? If you look at the thickness, they're all thickened. So this is dilation or expansion of the white areas using that rectangular element. And here is what? The erosion of the white areas, right? So erosion and dilation are extremely simple. Next is opening and closing. Opening is an erosion followed by dilation. Closing is the opposite, dilation followed by erosion. And here, since you're eroding, then dilating, in that erosion part, you're going to get rid of the noise. And then by dilation, whatever that you made thin, now you're going to give back the thickness to them. So this dilation is going to reverse the effect of erosion and give the original thickness back, but since you're eroding, small noises going to go away in the first step. So this is not affecting the thickness of the white areas, but getting rid of the noise. On the other hand, if you first do the dilation, then the erosion, what's going to happen? In the dilation stage, if there are small holes inside the object because of dilation, they're going to be filled. And then when you do erosion, that thickening is now going to be canceled or neutralized by this thinning. So you get the original thickness back, but during the dilation, you filled in the small holes. Okay, so you see that using opening and closing, I can achieve different things. One, to remove the small noise in the background. One, it's to fill in the small holes in the foreground. Okay, and then the difference between the dilation and erosion, the difference between them, so one of them, make a dilation image, make an erosion image. So one of them is going to make the boundaries thin, one of them is going to make the boundaries thick. If you subtract, basically you are going to get boundaries. And so the gradient image is going to be a what? A boundary image, the edges, the thick edges of the image. Now, the opening, the closing, and the gradient, you don't apply a command like CV2 erode or dilate. So you don't have something like CV2 open, CV2 close, CV2 gradient. You don't. Instead of that, you use a command called CV2 morphology EX. Okay? And then inside this guy, you pass your whatever you want to do operations on. So I'm passing copies of binary. And then you say, what is it that you want to do? Do I want to do CV2 morph open? Do you want to do morph close? Or do I want to do morph gradient? There is also top hat, bottom hat, and so on. But I find these guys a lot more interesting than those top hat and bottom hat. And then you pass a kernel, and then it is going to do what? These operations for you. And here you can see them. This is the original image, this is the opened, and this is the closed. And if you look at the comparison between binary and open, what is it missing? Yes, look at these 5 white pixels, the noise background, they are gone. Now, if you compare this against what? Against closing, what do you have? Look at that. 4 small holes here, 3 small holes there, they are all gone. And out of 3 small holes here, 2 of them are gone. This one was too big for that size of the kernel to go. Okay, this size of the kernel, the width of it was not enough. The width of it is not like 3 pixels or so. This is a wide thing. So if I want to get rid of that, I need to go back here and change this probably to 6 or 7 or something like that. And then hopefully that can remove that hole as well for me, right? Because that guy was too deep in the horizontal direction. So let me show you that. This is the open, this is the close. You see, now that one is also gone. Good. And if you want to do something very nice, actually, if you have both noise and the holes, I would do an opening followed by a closing, right? That way, I'm gonna take care of everything in one command, and I can show you that. But before that, I want to show you the gradient command. Look at this. This is the gradient command, which shows me the boundaries. And because of all this noise and holes, I have a lot of extra boundaries. So really, if I want to apply this gradient command, what I better do is first do opening followed by closing, get rid of all noises and holes, then apply the gradient command. That is going to give me a beautiful boundary with a lot of these unwanted boundaries gone. So look, what I do here is, you see here, I did this opened, right? I opened the image. Now, instead of copy of binary, I passed the opened to the close, right? Here. So I do something here. I'm gonna call the closed one that I'm gonna pass the opened to it. And then I'm gonna pass this closed one to the what? To the gradient. That way I'm gonna have a beautiful image, right? Let's take a look. And I can see that closed one as well. If you want, I can show you that closed one. So let me go ahead and say image opened, then closed, and say closed one. Okay, and you're gonna have some beautiful thing. So right, let's go ahead, look at the gradient, look how beautiful it is. And this is the opened, then closed. Look at that, look how beautiful they are. You see, it's extremely beautiful. The noise is gone, the holes are fixed, the thickness is almost intact, and now my boundaries are very good boundaries. You see, that's the power of what? That's the power of morphological operators to give you what? To give you a beautiful final image. So hopefully this lecture was useful to you and you learned how to binarize images, how to work on them, and so on. And I'll see you in my next lecture. Thank you.